All right, so we're going to talk about the direct comparison test and the limit comparison test. And these are very similar. The process is the same, actually. Conclusions are a little bit different. Very similar to what we did in Chapter 8. We had these two tests in Chapter 8. So far we had pretty simple tests. P-series, geometric, those are easy rules to figure out if a series converges or diverges. But there are a lot of series that are similar to a P-series or similar to geometric that aren't quite those. And so we can't use those quick tests. Rather than always going to an integral test, which sometimes is not so bad and sometimes is terrible, we can compare these unknown series to series that we do know, geometric or P, and try to do some sort of comparison. Okay, so you might have to pause my video to copy down what this says. So if so, do that. Otherwise, I'm going to carry on. Start with direct comparison test. This is the one where you're comparing two series. Now, there's a slight stipulation here. Let's make sure that sequence, the terms in sequence B are larger than the terms in sequence A, and both of those are positive. All right, so if the larger series converges, then the smaller series converges. Remember we had this visual? Let's put labels here. This is a larger series. Red is a shorter series. So if the series for B sub n is converging, if it's decreasing fast enough to converge, think of it as pushing down on the smaller series, then it must be going fast enough down to converge as well. And if the smaller series diverges, then it's kind of, think of it as pushing up. Think of A sub n as pushing up on B sub n. So it's forcing it to diverge as well. Where you get into trouble is like, okay, well, what if the smaller series converges? What does that tell me about the bigger series? Nothing. What if the bigger series diverges? What does that tell me about the smaller series? Nothing. So if DCT is inconclusive, then use the limit comparison test. Now, it should work out that you could always use the limit comparison test, but remember, some of the multiple choice questions might say, oh, converges by direct comparison test, or diverges by whatever, so you have to know whether this can be used or not. All right, so what if it is one of those weird situations where we know the larger series diverges, which doesn't help us with the smaller one, or we know the smaller series converges, doesn't help us with our larger one. So again, let's say that we have positive terms in both series. Then, and let's say that our A is our unknown series, and let's let B be a known series. So remember, we did this in Chapter 8. We take the limit as n approaches infinity of our unknown divided by our known. This usually gets us to a horizontal asymptote situation. If you get a number, some number between 0 and infinity, then the two series act together. They both diverge or they both converge. If your limit is 0, then the unknown, spelling unknown wrong, the unknown converges if the known converges. But if you get a limit of 0 and you know that the known one diverges, then that's inconclusive. And finally, if you have something top heavy and this comes out to infinity, the unknown diverges if the known diverges. Okay. Limit comparison test, it should be try or at least think about DCT. I always show a comparison step. And then if I realize that that comparison step isn't going to help me at all, then I switch to setting up LCT. Simple as that. Both of them start by comparing your two known and unknown series. All right, so let's practice. It's just converge or diverge by what test? We do not, if these values, If we get converges, we don't know what they converge to. All right, so 2 over 3 to the n plus 4. This is a lot like just 2 over 3 to the n. So cut off the plus 4, right? All right, so I always do compare, just like I did in chapter 8. Compare in any order, 2 over 3 to the n plus 4. Compare it to 2 over 3 to the n. Same numerator. The plus 4 is a larger denominator, smaller fraction overall. Okay, and then what do you know? Well, I know that the sum from 1 to infinity of 2 over 3 to the n, if I want to rewrite that, that's, if this helps you, although you probably know this if you already picked it to set up, that could be written as something more geometric looking, 2 times 1/3 to the n. I know that this series converges. It's a geometric series, it converges. You don't have to say what it converges to, it's just, you know, this geometric series converges. Now, if the bigger series converges, it's pushing down on the smaller one, forcing it to converge too. That's how I think of this. So I can say, therefore, this series converges, my unknown series converges by, I'm going to let you say DCT, but you should write direct comparison test or find the words direct comparison test on your multiple choice. Okay, easy as that. And the reason we think about direct comparison is because it's nice not to have to write the limit notation, right? You can just say, oh, yep, good. All right. Okay. This looks like one of those harmonic series, but we know for sure that the 1 over n or 1 over 5n would be a convergent harmonic series. This plus 3 is kind of different. So let's compare 1 over 5n plus 3. Compare it to just 1 over 5n. I always just cut off the extra term. The fraction on the left is smaller. Denominator is bigger. What do I know? I know that the sum from, I always just match these terms, 1 to infinity of 1 over 5n diverges. That's just 1/5 times the harmonic series, right? So I know that that diverges. Now here, the bigger series diverges. That doesn't affect the smaller series, okay? So DCT fails or is inconclusive. So now I have to say limit comparison test. The limit as n approaches infinity of my unknown, 1 over 5n plus 3, over my known, 1 over 5n. What does that simplify to? Well, that's the limit as n approaches infinity of, it would become 5n over 5n plus 3. And that horizontal asymptote is 1. Go back to our rules. If we get a number, then these two series act together. If we got 0, we'd be inconclusive because the thing that we know diverges, so we would have had to go back to the drawing board and probably do integral test. Anyway, we got a number, which is great. So I can say, therefore, series, they act together. So this series, the unknown series, diverges by a limit comparison test, LCT. Why do these tests work, by the way? Off the top of my head, I can't remember, but there was a good video that I think I've linked from YouTube, like I always say. But yeah, there are some pretty good explanations of people who can do this with visuals in a much better way than I can explain it. All right, continuing on. 1 over 2 plus square root of n. Compare. Let's just drop off that constant term. So looking at 1 over 2 plus square root of n, compare that to 1 over square root of n. Fraction on the left is smaller. What do I know? I know that the sum from 1 to infinity of 1 over square root of n, that's a p series. It's a divergent p series because p is only 1/2. That's divergent or diverges. The bigger series diverges. That does not help me, so I need to use limit comparison test. The limit as n approaches infinity of 1 over 2 plus radical n over 1 over radical n. That is going to be the limit as n approaches infinity of radical n over 2 plus radical n. I do believe you can skip right to this step. I might do that in my homework, by the way. But just to be safe, showing where that came from is 1. It's almost always going to be 1 unless you start changing, like if you made this 2 over square root of n or something like that. Anyway, that's a number, which is great. So I can say they act together, so diverges by LCT. All right, next one. Compare 1 over n squared plus 1 compared to 1 over n squared. Left side is smaller. What do I know? I know that the sum from 1 to infinity of 1 over n squared is another p series, but this one converges since p is greater than 1. The bigger series converges, pushes down on the smaller series. So I can get right to my conclusion and say, therefore, my unknown series, they act together, also converges by DCT. Next one. Square root of n over n squared. Now, we always cut off this term, right? Let's still keep by that rule and see how we can manipulate this a bit. 1 over square root of n plus, square root of n over n squared plus 1. Let's just compare it to square root of n over n squared. Comparison, I can see that this fraction is a bit smaller. Instead of keeping this for what I know, instead of keeping it as n to the 1/2 over n to the second, why don't we go ahead and subtract those exponents? 1/2 minus 2 is negative 1/2, or 1 over n to the 3/2. That's a p that's greater than 1. That series converges. The larger series converges and pushes down on the smaller series. So, therefore, smaller series converges by DCT. Okay, what about this crazy one? N times 2 to the n over 4n cubed plus 1. All right, so let's compare just by knocking off plus 1, right? N 2 to the n 4n cubed plus 1 equals n 2 to the n over 4n cubed, smaller. Well, what do I know about this guy? So let's see. Let's simplify that known. Instead of n over 4n cubed, I'm going to make this 2 to the n over 4n squared. Now, what do I know about this series? The exponential numerator will grow faster in the end than the quadratic denominator. So by nth term test, I know that this diverges. The terms are not approaching 0, they're growing infinitely. I'm just going to write nth term here. Unfortunately, the bigger series diverges. That doesn't tell me about the smaller series. So I switch over to limit comparison test. The limit as n approaches infinity of my unknown divided by my known. Maybe we could say this, times the reciprocal of my known. Okay, where does that get me? Well, you have 4n to the third. 2 n's cancel. 4n to the third over 4n to the third plus 1. It's going to come out to roughly 1. I used my simplified version. You could have gone back to this one, but you'd get the same conclusion. So again, we get a number. The two series act together. In this case, the series diverges by limit comparison test. Anytime you get this like ugly kind of series, I think that one was kind of ugly, it's probably going to be limit comparison test. It's nice because you get to end up kind of ignoring the other terms. So we're not going to do all of these, but what would I compare this to? I would compare it to just 1 over 3n squared. And even though 1 over 3n squared is, let's see, this is a minus 4n right here, so this fraction here, 3n squared, it should end up being, let's see, this denominator, so the plus 5 is insignificant at infinity. So smaller denominator here is bigger fraction overall. So I know that this converges, but if the smaller one converges, that doesn't help me with the bigger one. But I can still use LCT, right? And so here I would compare this one as 1 over square root of 3n. This fraction is bigger, right? I can do a little limit comparison because this is not a true p series. So, well, actually, no, yeah, it is. I could do this. I know that my smaller, I could do direct comparison test on this one. My smaller series is going to diverge, and so therefore, so will that one. Oh, no, wait, you know what? But it's, just kidding. That's a minus 2 down there. So this fraction here is smaller denominator, bigger overall, excuse me. So yeah, you would need limit comparison. And finally, I could just say, oh, let's look at n squared over 4n to the 5th, which is practically 1 over 4n to the 3rd. So I have this p series that converges, and it is ultimately going to be a bigger fraction than the unknown. So this is the one I could do direct comparison test with. All right, that's it for today. Your homework should be number 16, and we have this practice worksheet. So I will be collecting this and grading it in your homework grade.